Welcome, everyone. Today we're going to be doing quantum teleportation, the famous quantum teleportation. So, what is quantum teleportation? Well, the first thing it's not is teleportation. It's kind of more like the inverse of what we did with superdense coding. In superdense coding, we called it superdense coding because we showed that one qubit is worth two classical bits of information. In quantum teleportation, we're going to use some classical bits of information to send a quantum qubit of information to somebody who's separated by a classical communications channel. In superdense coding, we did the opposite, if you'll recall. Quantum teleportation, that is the circuit we've got up right here. Um, what it essentially means is that we have this original state here, psi, and psi is the quantum teleportation state. It's going to be teleported, right? And it is, in a sense, a little bit less cool than teleportation, but still up there in terms of quantum coolness. We're essentially going to take this state and we're going to make it appear here without any kind of quantum communications channel in between. The other thing we're going to send between Alice and Bob here is two classical bits, because remember, a qubit is worth two classical bits. So this here is just a Bell state. It can be any Bell state. In this particular problem, I've elected to choose the 0, 1 Bell state, which let's see, looking at my notes here, is 0, 1, 1, 0 is 0, 1 plus 1, 0. So we're going to use that to kind of teleport our qubit here. Apologies, still sick, still very sick. Take care of the throat. Okay, right, back to the quantum teleportation. I promised you teleportation, and I'm going to give you teleportation. Note this is impossible in classical physics. You can never do something like this without quantum physics. So how we're going to give it, we're going to begin here in the circuit with 3 qubits this time instead of just the 2. So it's going to be a little bit more kind of wonky to keep track of these things. Um, we're going to do it like this. We're going to start here in our initial state of these two guys combined. We're just going to call it this. We're going to call the first state we have size 0 before any gates have acted on it in any kind of way, right? And that's essentially just going to be this first bit. These diagrams are read from top to bottom. So this is the first bit, and these are the second 2 bits. And the first 2 bits are going to be Alice's bits, and the last bit is going to be Bob's bit, right? Bob's on the other side here. These are his gates. He gets to use these, and Alice is over here now. So she owns the first 2 bits, and Bob owns the last bit only. So size 0, this state is simply going to be this state compounded with this state. And by compounded, I mean tensor product, as always. And it's going to look like this. The state to be teleported, by the way, is going to just be a general qubit. The most general possible form of a qubit. It's just going to be that. Plus beta 1. That's all. So we want to teleport this state over to Bob. And they're separated by a classical communication channel over which we can only send classical bits. We can't send qubits over it. It's not a quantum communication channel. So let's tensor product these states together. Um, we're going to have this like this times the Bell state oh 01 plus 10 not 10 it's 10. That's just mnemonic. Don't pay any attention to that. Plus B1 be a constant. These two have to add to 1 again. Squared, a squared, alpha squared plus beta squared needs to equal to 1 because these are probabilities we're talking about. Times the beta state again. Rather, times the Bell state again. Beta is the symbol for the Bell state. Beta 0, 1 specifically is the Bell state we're dealing with teleportation with here. 1, 0. Right, so this is size 0. This is how we start here before we run it through any gates. And the first gate here is a control not gate. That's what that's a symbol for. This is the control bit here, and this is the bit that's going to be knotted or not knotted, or maybe a little bit of both, um, depending on whether we have a quantum state here, which we do. It's a qubit, so we're going to see a little bit of not and a little bit of not as well, right? Both at the same time. So this is our state to be teleported. We'll just remember it. It's here now. It's part of this Hilbert space. So the control bit is the first bit here, um, the state to be teleported. So this control bit is going to determine whether or not the first bit that it's acting on, it's only acting on this bit. It's only acting on the first bit. So these two bits, both of these bits that I've highlighted here are Alice's bits. This last bit here is Bob's bit. This is Bob's bit. He's over here. He's waiting for the transmission so he can use these gates if he has to. He might not have to. We'll see why later. This is an X and a Z polygate. They may be necessary later. So this is the control bit, and it's going to act here. So we're running this second bit through the NOT gate. These don't get flipped because this 0 control says not to flip them. And this part of the linear superposition, the control bit is a 1. So it says do definitely flip those guys. So what we're going to get out here in our psi 1 state, after the first array of gates is acted on this stuff, we get out this. No change here because this is a 0, so it says don't flip any of this, right? Nothing changes here because the 0 bit doesn't flip things. But in our second row here, we do flip the second bit because the 1 says yes. It's true. It's an affirmative bit. I'm omitting the normalization constants, by the way. Pay no mind to them. We won't be needing them for this. We'll just assume every state is normalized and that uniquely fixes the normalization constant. Plus 0, 0, right? So that's psi 1 after it's gone through the C naught. Psi 1. Okay, and now it's gone through this gate here, the psi 1 gate. Now we're ready to send only the first bit, this one here, also first bit through this Hadamard gate here to attain psi 2. Sorry, this mouse is not behaving right now. Psi 2, 2. Alice's first bit through the Hadamard gate. Even I lose track of the indexing sometimes. Alpha. All right, so we're sending this through the Hadamard gate. These two guys here, Alice's first bit. And the indexing should be read left to right. Alice's first, Alice's second, Bob's. 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 If you read this diagram here, this is Alice's first, Alice's second, and Bob's. And only Alice's first will be sent through this Hadamard gate here. What does a Hadamard gate do to a 0 bit? It does this. It turns it into this, halfway in between a flip with a 1 over square root of -2, or square root of 2, right? And then the rest is left alone. 0, 1, 0, 1, plus 1, 0, plus beta. What does a Hadamard gate do to a 1? Same thing, but a minus. 1, 1, 0, 0. Right? So now we're at this stage, right? Side 2. And now it's time to make some measurements. But before we do, I'd like to do some algebra on this to show you why these measurements are going to definitely be coming out a certain way. Let's see, we're rearranging in a certain way. Right. Right. I want to rearrange so that the first two are part of I want I want to do some algebra and rearrange here so that these first two qubits are part of the same little ket here. All right, so let's regroup terms so that this and this are part of the first ket, right? And this is part of the trailing ket. Okay, so 0 0 how do I have the alpha in the second ket? Yes, I do. All right. So all right, which term stack was 0 0? 0 0 alpha plus this, alpha 1, right? Alpha 1. And then I get it, pick up another 0 0 from here for beta 0, positive beta 0, right? Okay. Now we get another 0. All right, so 0 0 is done. Let's do the 0 1 terms now. 0 1. So 0 1 0, that's a positive alpha. 0 1, what did I do? 0 1 0. 0 1 0 for a positive alpha term. 0 1 0. 0 1 0 alpha plus, how do I make a 0 1 0 with, these are just permutations, by the way. Feel free to skip ahead if you're not interested in this algebra. 0 1 0 for alpha. How do I get it from beta? Um, beta 0 1 1. 0 1 1 is a positive. 0 1 1. 1 1 is a positive. Right. And now I want to make 1 zeros. How do I get it from alpha? A 1 0, a 1 0 1. That's positive. How do I get one from beta? A 1 0 1. It's going to be negative. 1 0 0 negative 0. It's going to be negative, not positive. And then finally, where do I get 1 1 terms from? Um, 1 1 positive 0 plus 1 positive 1 negative 1 again. 1 negative 1 again. Okay, good. So this is just rearranging. We haven't done any quantum operations on this at all. We're simply rearranging terms here to make kind of the measurement outcome more clear. Um, Now, Alice is going to perform a measurement. Alice is going to perform a measurement. And her measurement is going to determine which classical bits she sends, right? So let's say she does a measurement and she gets, which beta were we using? 0 1. All right, so the Bell state we were using was 0 1. If we get lucky and if we get lucky and we roll a 0 1 here in the quantum measurement dice, um that means that the state, which again we're not touching the state. We're just measuring these two bits right here. These are Bob's bits, right? These are Bob's qubits that he already has over here, right? We're not transmitting qubits. What we are doing is we're just measuring these kind of like classical bits over here, right? Okay, so we measure these bits, and if we get 0 1, we know that Bob has the correct state just kind of sitting over here. If we measure a 0 0, we know we have to do some operations. We know Bob has to do some operations on his state to get the right state out. And depending on what measurement Alice does on her side, she knows what operations Bob needs to do on his side in order to rectify the quantum bit to be the bit that we're trying to teleport slash clone, right? So what Alice can do now is transmit these two classical bits over to Bob, right, through the classical channel, and Bob will know what operations to do to get the classical bit. And then we've teleported a qubit successfully. So by doing this, we can teleport this qubit over this channel, and now Bob will have like know which operations to do in order to have the qubit. So we've teleported this. We've teleported psi over a channel. There's no qubits being moved anywhere. It just kind of moves to the other side. So we can do this with an arbitrary quantum state, any quantum state whatsoever. We can without any kind of channel to put it through, just have it appear there on the other side, right? This seems a little bit magical. But there are a couple of things to notice here. The first thing to notice here is remember what I told you about no cloning. Don't even think about it. Don't you dare do it. There's no cloning. So if you try to clone a state, you're gonna have to destroy the original. Have we done that? Yeah, we have, because we did this measurement here, right? We collapsed it to a certain thing. So by the point where we have the classical bits to transmit to Bob, there's no cloning because you destroyed your original state. So once psi pops up here and Bob has it on the other side, the original copy of it we have has been destroyed by our hands. Okay. The second thing to notice here is it seems like we're breaking locality here because we've teleported something right here, and teleportation kind of breaks locality. So why have we not broken locality? And in fact, I'll kind of like pause here for a second so that you can kind of like think about that, because this is an important question. It's interesting to think about. So take 30 seconds to think about why this hasn't broken locality. I'll be back. Oh, right. So the reason it hasn't, and you can pause your video if you're interested in figuring this out without me telling you, is that we have to transmit these classical bits. We have to transmit classical bits over a classical channel, and that classical channel has to obey locality, of course, right? If you think about it, classical bits can't move faster than the speed of light. They're just normal bits. There's nothing special about them. So, um, if you get lucky and we roll this 0, 1, then theoretically, like, yes, then you could do it. But you don't always get lucky and you don't always roll that. This protocol relies on Alice having to transmit her classical bits over there after these measurements, and then and only then can Bob 100% get lucky and not get lucky, just know which qubit he has there, and then we've successfully teleported the state. Without those classical bits, you only have a 25% chance of getting it right, and that's not a successful teleportation. So that's what kind of stops this from breaking locality. Although it definitely increases the chances. I mean, a 25% chance, that's not bad, right? But then again, we're also only dealing with an alphabet of 4 symbols, so that doesn't really help in any kind of way. It's still random chance. So sadly, we can't really break the speed of light or do a real teleportation, even though a lot of pop sci people like to go on and on about quantum teleportation. It's not real teleportation. I'm sorry to break everyone's heart there, but c'est la vie. I'll see you guys next time. Cheers.